Hello everybody, this is our video solution to problem 8 from the fall 2021 Math 302 final at Cal State Fullerton. Let's see, we're sticking with groups in this problem. We are letting G be S4, so this is the group of permutations of the set 1, 2, 3, 4. Note, the group is not the set 1, 2, 3, 4, but rather the group of permutations, so there's actually 24 different elements in this group. Determine which of the following subsets of G is a subgroup of G. And then we have to explain why. Okay. There's a hint. Let's see. Only one of them is a subgroup. Okay, so 3 of these are not going to be subgroups. So before we dive into these, let's recall a few things that we know are going to be necessary if you're going to have a subgroup. So if I have a subset H of G, for H to be a subgroup, we need, all right, so first, the identity element needs to be in H. Okay, that we know has to happen. Second, if I have 2 elements of H, then their product or composition, however you like to write it, also has to be an element of H, so closed under the group operation. In this case, there really would be composition. And 3, if A is an H, then A inverse has to be an H. So the subset has to be closed under inversion. So if you're trying to rule out whether that a subset is a subgroup, it's really good to look at these and say, oh, maybe I can toss something out for that. For example, let's check these 4 examples and see if one of them doesn't have the identity. So let's see. This one does have the identity. Contains the identity. Okay, so that's okay. Oh, it has the identity. Oh, that's not good. Well, look at this. D has no identity element. There we go. So not a subgroup, since E is not an element. Okay, cool. So we can rule out D as being a subgroup. All right, next we need to make sure that each of these is closed under products. So let's look at this first one. Let's see, so I have the identity element E. Then I have 2, 3, 4, and well, let me try multiplying it by itself, say. So 2, 3, 4 by 2, 3, 4. Let's see, 2 goes to 3 goes to 4. 4 goes to 2 goes to 3. And so then 3 has to go back to 2. Let's double check. 3 goes to 4. 4 goes to 2. So the product is 2, 4, 3, which actually is in there. This is nice. Let me just give a name to this quickly, right? Let me call this x. 2, 4, 3 then is x squared. And so since this is a 3 cycle, we know it has order 3. So x cubed is equal to the identity. In fact, what that means is that this is the cyclic subgroup generated by 2, 3, 4. Oh, wow, so this is a subgroup. Well, look at that. Okay, so this one works. In fact, that's the one that is a subgroup. But of course, we got to explain the rest. All right, now this second one, a subset of order 7 that contains the identity, we don't really know a priori if it's closed under products because it doesn't say. So let's put that one on the back burner for the moment. How about C? C, well, okay, I know multiplying by E doesn't do anything, but let me square 1, 2, 3. In fact, it should look a lot like what happens with 2, 3, 4. This should be 1, 3, 2, right? It's just going to swap the last 2 entries, and you can double check it. 1 goes to 2, 2 goes to 3, 3 goes to 1, 1 goes to 2, 2 goes to 3, back to 1. All right, so this is true. But 1, 3, 2 is not in the set. Right? This is not an element of E, 1, 2, 3, which means this subset is not closed under multiplication. So not a subgroup, since we'll just say it fails to. That'll be a little shorter. Okay, so not C. So how about B? Now, we could say, well, we didn't know about the products. How about the inverses? And we kind of have the same problem here, right? We really don't know a whole lot about this subset, right? Because it's given very descriptively just in terms of, well, it contains an identity. That's good, but just the size of it. And this is where we can employ Lagrange's theorem. So recall Lagrange's theorem tells us that if G is a finite group, and H is a subgroup of G, then the order of H divides the order of G. Okay, well, in this case, we have a subset of order 7, and the group G has order, we said, 24, right? 4 factorial. So if this subset was going to be a subgroup, it would have to have order that divides 24. But 7 does not divide 24. And so this set is not a subgroup, since 7 does not divide 24. And we'll cite Lagrange here. So we can rule out B. And there we go. A is really the only one of these subsets that is a subgroup. All right, everybody, we'll see you next time.